In this video, I'm going to talk about seismic sources and receivers. We learned that using seismic data, we can obtain a detailed image of subsurface. And the first step in any seismic data surveys is data acquisition. And for data acquisition, we need seismic sources and receivers. First, I'm going to talk about seismic sources. Different sources have been developed for both land and marine seismic data acquisition. A seismic source produces some energy, and that seismic energy travels down through the earth and hits different geological boundaries, and a fraction of that energy is bounced back to the surface. And this is how we are able to image different geological layers. And that energy is transmitted through the earth in the form of seismic pulse. Dynamite is a popular source that is used in land seismic surveys. And to use dynamite, usually we drill a small hole. And the depth of the hole should be equal to the thickness of the soil. And in the bottom of the hole, we place a charge of dynamite and then fill the hole with gravels, fragments of rocks, and mud. And then we fire the dynamite. There are so many advantages of using dynamite. First, it produces high quality data. And usually the data that we get from dynamite has very good signal to noise ratio. In addition, it is portable and we can use it almost anywhere. We can use it in mountains, in marshes, swamps, and wetlands. And finally, it has very good penetration depth, and using dynamite we can study deep formations. The disadvantage of dynamite can be related to some safety concerns. For example, we may not allow for using dynamite in residential areas. What you see here shows how we use some rigs in order to drill a hole for dynamite. For example, in mountains area, the rig is portable, and as we see, we have no restriction to use dynamite. Now, just let me ask you an insightful question. Why is dynamite placed below the weather layer? So the reason is that the weather layer is highly attenuative and it attenuates seismic signals. So by placing the dynamite below the weather layer, we can improve seismic data quality. Vibroseis is another source that we use in land seismic surveys. Vibroseis is a truck, and in the middle of the truck there is a huge plate, and there are several arms that control the plate. So these arms push the plate against the ground to enhance coupling, and then that plate vibrates and produces seismic energy. And this is how we are able to record our seismic data. There are several advantages of using dynamite. First, it is repeatable, so it means that for the same data acquisition parameters, we can produce one shot record over and over, and then we're going to have several shot records with different noise components but the same signal components. So by stacking those records, we can improve signal to noise ratio. Also, there may be less concern about safety, so we may use it in residential areas, and we don't need to drill a well for Vibroseis, so it may result in a faster data acquisition. If I want to talk about disadvantage, first of all, it cannot be used in, for example, mountains, in swamps, in wetlands, and also there should be a road system in order to move Vibroseis. Another disadvantage of Vibroseis is that it produces a lot of ground rolls, and ground rolls in reflection seismology is noise, and we want to avoid it. So this is another thing that we should consider when we use a Vibroseis. Something that you should note here is that the pulse that is produced by dynamite is different from Vibroseis. So in other words, a dynamite produces a localized wavelet as similar to what you see here. So for example, if we have such geological models with three geological boundaries, then if we use a dynamite as a source, the reflection image will look like something like this. For each geological boundary, we're going to have one reflection, and this is how we are able to identify them. But the signal that is produced by Vibroseis is not a wavelet, it is a waveform or a wave train, and it is called chirp. So a chirp is a signal whose frequencies increase or decrease with time, and as a result, a trace that we get from a Vibroseis for this geological model will look like something like this. So as you see, it is not that interpretable compared to a trace that we get from dynamite. So how can we address this issue? We use a mathematical operation that is called cross correlation. Assume that we have two signals, W and S, and the cross correlation of W and S is given by this equation here. T and tau both are time, and tau is a dummy variable. And cross correlation measures the similarity of two signals as a function of time. Now just let me explain how we can use cross correlation to address this issue. So assume that here is a pulse that's produced by the Vibroseis, and if we cross correlate it with itself, then we're going to end up a localized wavelet. So this wavelet is very similar to what is produced by a dynamite. So in other words, assume that we have our Vibroseis record, and then what we need to do, just cross correlate the Vibroseis signal, and we know something about Vibroseis signal because signal is a controllable source. We can design its waveform, its wave train, and we know about it. So what we need to do, just we cross correlate the waveform that's produced by Vibroseis with a raw Vibroseis record, and the output will be something like this. So in other words, the output will be some localized wavelet that if just we look at this trace, you can easily interpret subsurface. Another source that is used is weight drop. There is a truck, and behind the truck a heavy weight is suspended, and this weight is dropped to produce a strong seismic energy. However, compared to dynamite and Vibroseis, this source may not be that strong, so it should be used for shallower target. Also, we may use a sledgehammer when our target is very shallow. For example, we want to study soil or just few meters below the surface, and what we do, we need a sledgehammer to strike the ground to produce seismic energy. For marine seismic data surveys, we use air gun, and an air gun is composed of two chambers. One chamber that you see here, another chamber is here, and there is a piston within this chamber. So this chamber is filled by air, and then this piston compresses the air to increase the pressure, and once the pressure gets to 2000 psi, the piston is unleashed, and high pressure air is released from these holes, producing a strong seismic energy. This image shows a typical air. You may get some idea about the size of an air gun. Something that I should mention here is that we never ever use a single air gun. We usually use an array of air guns, so several air guns are used at the same time, and there are several advantages of using this technique. First, we produce a stronger seismic signal, more energy. The second thing, we know that once the air is released to the to the water, it produces some bubble, and bubble, goes through several contraction and expansion and contractions. And as a result, it may produce some artifact that is called bubble effect. And bubble effect will degrade our seismic data. If we use an array of air gun, then we can avoid also the bubble effect. The receiver that we use for land seismic surveys is called Geophone, and in very simple model, you see that Geophone is a magnet, and over the magnet there is a coil that is suspended by a spring. And here we have a spike to insert into the ground for coupling. And once the earth vibrates, this coil oscillates up and down, and we know that according Faraday's laws of induction, it produces some electricity, and that electricity is transmitted to the recording system, and this is how we are able to record ground motion. What you see here is a kind of vertical geophone, but horizontal geophones are also available to record the horizontal motion of the earth. In addition, 3-component geophones are also available. They record the vertical motion in addition to 2 horizontal motion, south-north and east-west. For marine seismic surveys, we use hydrophones. Hydrophones are made from piezoelectric material, and piezoelectric material produce electricity when they are subjected to pressure. And so when seismic waves passes through a hydrophone, we're going to have some change in the pressure, and as a result, some electricity is produced. This is how we are able to collect marine seismic data. Something that I should emphasize here is that although geophones and hydrophones record seismic data, they record different parameters. Geophones record motions or ground vibrations, but hydrophones record change in the pressure. So in terms of what they measure, they are different, but in terms of the data that we get and how we interpret them, they're almost similar. How do we acquire seismic data? We deploy an array of geophones, and usually we start data acquisition by placing the source in either side of the array, and then we move source forward. So here three angles represent geophones, and here we have shots. So what you see, we're going to have the first shot, and this is how we start our data acquisition. Then once we record seismic data, then we move the shot forward, then we're going to have another shot record, and then continue shooting. So we scan through the entire array. At the end of the day, we're going to have several shot records, and by processing all of these records, we are able to obtain some image of subsurface. So here I wanted just to mention how we record seismic data. So what you see is an array of geophones. So we place a source here, and then we fire it. And once we fire the source, you see, or activate the source, we record the ground motion simultaneously as a function of time. So the output of seismic data is a 2D function, and so one of them is time and another is distance that corresponds to the geophone location. For marine seismic data acquisition, an array of geophones is placed in a tube, and usually we have several tubes that are towed behind the ship parallel. And so the reason why we use several tubes in order to obtain 3D seismic data. And you see that here right behind the ship there is an air gun. So the air gun is activated and produces some seismic energy, and we record those energies through several arrays of hydrophones that we deploy parallel to each other. Something that is interesting is that marine seismic data acquisition is mobile. It means that the ship moves slowly, about 4 to 5 knots, and continuously records seismic data every 6 to 13 seconds. In reflection seismology, the pulse that is produced by a source is also called wavelet, and wavelet means a small wave. And the reason because the pulse that is produced by a source has very short time duration. And we see subsurface structures through this seismic wavelet. We learned that if we have such a geological model, then the seismic image will be something like this. So we should be able to identify different geological structures through seismic wavelet. And in order to facilitate this process, geophysicists have developed different display methods. One display method is Wiggle display, and the Wiggle display is very simple. So assume that you have a pulse, and in your seismic section, you color the area with positive polarity with black and leave the negative polarities untouched. So this is called Wiggle display, and it was invented many years ago when computers weren't that powerful and they didn't have a strong graphics. So it was a simple method to display seismic data. You may prefer to color the negative polarity and just leave the positive polarity untouched. So this is something that up to you. This image shows raw seismic section, and this shows the seismic section with Wiggle display. And I believe that even just while looking at this simple example, you easily note that there are several features that can be more easily distinguished in the Wiggle representation. If we have two geological boundaries, this is something that we get from the seismic image. So in the boundary between two layers, we have a strong reflection. In addition, it is possible that we have some noise in our data, and also we may have some artifacts. So as a geophysicist, it is a huge task to just identify the real structures and not misinterpret artifacts or noise. So now just let me ask you a question. Find 3 geological structures in this seismic image. So you may see some unconformity here, one anticline and several faults. It is something that I should emphasize. The more you're used to looking at seismic records, the better you can interpret seismic data and identify different geological structures. So Wiggle display belong to some times that computers weren't that powerful. It doesn't mean that it is not used anymore. Still, some geophysicists prefer to use Wiggle display, but other displays are also available. For example, we may use grayscale, or we may use color display, in which each color represents a specific amplitude, or we may use 2 color displays. So we show the positive polarity with red and negative polarity with blue, and the intensity of the blue and red color correlates with the amplitude of seismic data. So whenever the amplitude is high, we use more intense blue and red colors, and whenever the seismic amplitude is weak, we use pale red and blue colors. I hope that you have enjoyed the lecture and got some idea about seismic sources and receivers and how we do data acquisition. Thank you very much for your attention.